welcome to the first class in the GCE bootcamp. The GCE bootcamp is where we're going to prepare you for the alternative to practical paper in chemistry. This paper contributes 40% of your grade and it has just 3 questions. So 3 questions will account for what is going to be 40% of your final grade. So we cannot afford to not take this paper seriously. But the good thing is it has just 3 questions like I stated earlier, and these questions, the topics are known way ahead of time, literally covers the same thing year in, year out. So if you pay attention, attend the 3 classes that you're supposed to attend per week, do your class works, and you're going to be fine. That is our promise to you. Today, what we're going to be learning first is stoichiometry. You might be wondering, why stoichiometry? Because stoichiometry is the foundation of all chemistry reactions, and it is even more important when you're going to be writing an exam that has a practical paper like the GCE or even WAEC chemistry. So understanding stoichiometry is going to help you be able to answer questions on volumetric analysis or titration accurately. So let's jump right in. So what is stoichiometry? Stoichiometry is the part of chemistry that tells us the combining ratios of reactants that we have and the amount of products that we have formed. So basically, stoichiometry is how we measure how much reactants go into a reaction and how much product we have. There are so many ways by which we are able to measure how much reactants we use in a particular reaction or how much of product are we forming. Basically, how we quantify the reactant and the product. So for example, if you want to have, let's say, cereal for breakfast, so stoichiometry in that sense would be how much of cereal are you adding to your bowl and how much of milk are you adding to your bowl. You might be doing 3:1 depending on how you like your cereal, like you're taking 3 parts of cereal and 1 part of milk. So that is what stoichiometry is to us in chemistry. That is stoichiometry is how we quantify the amount of reactant that is going into a particular reaction and the amount of products that we're getting out of a particular reaction. Stoichiometry also helps us to understand how much of a particular reactant do we really need for a reaction. That how much of atom A do we need to form product C? How much of atom B do we need to form the same product? We're going to see an example now. One of the ways by which we use stoichiometry or measure stoichiometry in chemistry is by using mole ratios. That is, what is the mole ratio of the reactant to the mole ratio of that of the product? And that is actually how we balance chemical equation. So by the time you balance the chemical equation, you're going to have the total number of atoms of a particular element on the reactant side will be equal to the total number of atoms of the same element on the product side. So let's look at the molecular coefficient of this reaction. So we have here hydrogen gas combining with oxygen gas to form water. So the coefficient of hydrogen here is 2. So that means we have 2 moles of hydrogen. So, and we know that 1 mole of hydrogen has 2 atoms. So each of these white balls here is hydrogen. So they are connected together by a bond to indicate that it has become a molecule. So this is 1 mole of hydrogen. This is another mole of hydrogen, and in that mole you have in those 2 moles you have a total of 4 atoms. 4 times 2, 4. So you have 4 atoms here. So we have 2 moles made up of 4 atoms for hydrogen. Oxygen, the coefficient here is 1. That is, we have 1 mole of oxygen. 1 mole of oxygen is made up of 2 oxygen atoms. Again, each red ball represents 1 oxygen atom. So this is our 1 mole of oxygen gas. And when these 2 combine, what do we have? We have 2 moles of water. Here is 1 mole of water, oxygen combined with bonded to 2 hydrogen atoms, and this is mole 2. So here you can see the mole ratio of this simple reaction. We have 2 moles of hydrogen gas combining with 1 mole of oxygen gas to give us what? 2 moles of water. Earlier, we look at how we can use mole ratios to determine the stoichiometry to see the combining ratios of reactants to form a particular product, a particular reaction. Another way we apply stoichiometry is by looking at the relationship between mass and volume in a chemical reaction. At times, you quantify how much of a reactant you have used by volume, especially for gases, and you can work back to the mass of the material using this relationship. Bear in mind though, when you're working with volumes in chemistry generally, check for this caveat if it has STP, that is, if there is standard temperature and pressure. At STP, 1 mole of any gas will occupy 22.4 dm cube of volume. That is, at STP, 1 mole of any gas will occupy 22.4 dm cube volume at STP. This is such an important caveat to add that this only applies at STP. Only use this formula at STP. So if 1 mole of the gas occupies 22.4 dm cube at STP, then if you know the volume, you can calculate the number of mole at STP. If you know the number of mole, you can use this relationship to calculate the volume. But this only holds at STP. Now, let's look at if you're going from mass to volume. By now, I expect that you know how to calculate the number of moles using mass over molar mass formula. If you don't, we've made a poster for you on how to calculate the number of moles. If you join the GCE community, which the link is going to be below, you can actually enjoy this free class and even more in our GCE bootcamp. So let's look at the formula. That formula is number of moles is equal to mass divided by the molar mass. So if you know the mass of a reagent, if you divide that by the molar mass of that reagent, you're going to get the number of moles that are present in the mass that you're working with. So with these two, we can compare from mass to volume. So let's say you're doing a reaction that gives off a gas. How do you quantify the volume of the gas that has been given off in that reaction? If you know the mass of the reactant, you can work with this to evaluate the volume. Let's take an example. Example 1. It says that what volume will 88 grams of CO2 occupy at STP? Example 1, we're asked to calculate the volume that 88 grams of CO2 will occupy at STP. Here we've been told it is at STP, so we can always use this formula, right? But before we can use this formula, we need to find the number of moles because we've been given mass. What have we been given? Mass of CO2, 88 grams. Volume, we don't know. What is the condition? STP. So what we need to do first is find the number of moles that are present in 88 grams of CO2 and then use that to calculate the volume that will be present. But before we use this formula, we're going to use the formula mole is equals to mass over molar mass. We already know the mass. It is 88 grams. We don't know the molar mass. Let's calculate the molar mass. Molar mass of CO2 will be equal to the mass number of carbon, it is 12, we've been given, plus the mass number of 2 atoms of oxygen, because we have 1 carbon, that's why it's just 12 times 1 basically. 12 times 1 plus CO2, 16 times 2. So what do we have here? We have 12 plus 32. This will be 44 grams per mole. Your unit is very important. Without the unit, your answer is not valid. So we now know that the molar mass of CO2 is 44 grams per mole, right? Now let's go back to calculate the mole. So mole is, again, mass over molar mass, which here is, the mass we've been given is 88 divided by the molar mass, 44. So the number of moles is equal to 2 moles. So 88 grams of CO2 has 2 moles. What is the volume? We know that 1 mole of any gas is equals to 22.4 dm cube at STP. And we've been told this is at STP. So we can use this formula. So if 1 mole is equals to 22.4 dm cube, then what will be the volume when we have 2 moles will be X. That's what we don't know. If we cross multiply this and make X the subject of the formula, this will become X will be equals to 2 times 22.4 divided by 1. And X will just be 44.8 dm cube. So our final answer will be that 88 grams of CO2 will occupy 44.8 dm cube at STP. Now, let's look at if you're going from mass to volume. By now, I expect that you know how to calculate the number of moles using mass over molar mass formula. If you don't, we've made a poster for you on how to calculate the number of moles. If you join the GCE community, which the link is going to be below, you can actually enjoy this free class and even more in our GCE bootcamp. So let's look at the formula. That formula is number of moles is equal to mass divided by the molar mass. So if you know the mass of a reagent, if you divide that by the molar mass of that reagent, you're going to get the number of moles that are present in the mass that you're working with. So with these two, we can compare from mass to volume. So let's say you're doing a reaction that gives off a gas. How do you quantify the volume of the gas that has been given off in that reaction? If you know the mass of the reactant, you can work with this to evaluate the volume. Let's take an example. Example 1. Another way we look at stoichiometry is mole to volume. We saw mass to volume earlier, where we used the formula to calculate the moles and then go to volume from there. You can go directly from moles to volumes. Some questions will be like that, where they would have done the bulk of the work for you, where you'll be given the moles and you'll be expected to go to the volume. And if this has been specified to be at STP, makes your work easier. You just slot the values into that formula and you're good to go. So let's look at some of these examples here. We have 2 examples here on how to go from mole to volume. So the formula again is 1 mole of any gas at STP will occupy 22.4 dm cube of volume. If it's at STP, easy peasy. So what the question here is, how many dm cube will 3 moles of hydrogen gas occupy at STP? Again, it's been stated that it is at STP. You know 1 mole of any gas will occupy 22.4. So how many moles, what will be the volume of 3 moles of hydrogen gas at STP? It's just 3 times 22.4 dm cube. Easy peasy. That will be 67.2 dm cube. Another example is calculate the number of moles that are present in 44.8 dm cube of carbon dioxide at STP. It being at STP has made your work way easier. At STP, 1 mole of any gas will be 22.4 dm cube. If you have 44.8 dm cube, that means it's going to be 2 moles, right? So that is an easy conversion for you there.